Good morning, precalc fans. Welcome to a fine another Monday morning, sunny day outside. A little chilly, but oh, what a nice weekend it was. It was nice weather. It was nice to be able to get out and sort of enjoy the warm weather in a pair of shorts and a t-shirt, get some work done out in the yard. It was really nice. I hope everybody had a good weekend. I hope everybody's still safe and illness-free in your household. Once again, we continue to move and separate ourselves. We will get back to some sort of different normal, but we can get back to doing things again that we'd like to do. Once again, I hope everything's going well in your family. I've graded all your quizzes that you've handed in to me. You did an outstanding job. You've been doing a great job keeping up with the material. You've been doing a very good job with the evaluations. Continue to do that work. Once again, what you're learning here is a growth mindset, is that you don't have to be sitting here in the classroom to be able to learn certain things. You can still do this on your own and through the videos and take notes and do things through the videos and still be able to learn, which is a very good job. Because once you get to college, some of you will be taking online classes and you'll be exposed to things like this. So there's still in-service stuff that I do that I have to watch videos and be able to do some evaluations with it also. So you've been doing a very good job. Keep up the work. We're almost done with what we're going to be dealing with here. So just keep up the material that you've been dealing with here. And once again, we'll be through May as quick as you know it. I mean, it will go very fast. So once again, keep up the work. Today, what we're going to work on is we're going to work on the idea of one of my favorites is vectors. Victor. We get to start working with some vectors. Going back to, once again, what we did in trig class. But we're going to take a different look at a way of labeling and showing a vector and adding the vectors, because all we did back in trig class was we used our laws, sines, and cosines to be able to add our vectors, Victor. We're going to use something a little bit different, because when there's more than two, using laws of sines and cosines is not very efficient, because there's a lot of work to be involved in that. So what we have to do is we have to learn other techniques to be able to add vectors, Victor, that are more than two, or just be able to look at them in a different way. And when you go into physics, we deal with this in an IJ notation. That's what, in component notation, that's what we'll look at today. Displacement, when you have a directed segment, that's a segment with specific length and specific direction. Displacement, velocity, acceleration, these are all vectors. Victor, if you remember back to trig class, what we did is we did directions to your house, and you wrote out a distance and a direction that you had to travel to get to your house. And those were all vectors. So when you talk about a segment that has a specific direction, these are vectors, Victor. We have to have an initial position. It is where you start. And you have to have a stopping position. The terminal position is where you stop. Okay, the initial position is the tail. The stopping position is the tip. But once again, if I go too fast to this, feel free to hit the pause button. I will not be offended if you stop me in midsection, a sentence, and then start back up again once you can catch up. If we have vector addition, I want to travel A plus B. I want to travel A plus B. So if I take a look, I'm going to just clone this because it's easier for me. I know you can, but I'm going to travel A this direction. This is where I start. This is where I stop. And then I'm going to travel B, maybe. Wherever I stop A, I'm going to start B. And I'm going to travel B. I'm going to start B here, and I'm going to stop it there. Initial position, terminal position. So I'm going to travel here, and then I'm going to travel here. Now, if you remember what we drew in at that point, we drew in what was called a resultant vector, Victor, which is the solution to the addition of the two vectors, Victor. So basically what we did, we had Little Red Riding Hood, went down to Grandma's house, and the big bad wolf took the shortcut way. We have to show our resultant vector. Vector signified by VR. Once again, if you just write those two things without the result in there, that is like on a quiz, writing 5 plus 4 is equal to 5 plus 4. We want the result, which is a value of 9. So we need to draw in the result. We can also talk about scalars, which is a coefficient to a vector that affects the length of the vector but not the direction. So we have up here, we have a coefficient to this vector A. Tells me I want to go 2 of A. So I'm going to clone this twice. Oopsie. There's 1A, and I'm going to clone this to give me a second A. So we have 2A. We just multiply the length, we doubled the length, and then we're going to, wherever we stop this, we're going to travel B. So there is B. And once again, we always want to draw in the result vector. Basically, it is a shortcut to the exact same path. I'm still starting here, I'm still ending up here. But what's a different way of getting from point A to point B? Okay, a different way to going from Little Red Riding Hood to Grandma's house. I could take a straight line way, or I could take the path to Grandma's house. And that should be all review that's a review that we did in tree class. Scalar is the coefficient, resultant vector is the solution to it. What we're going to work on in pre-calc class, just to give this a different flavor, is components. When you talk about the components, maybe, the horizontal and vertical lengths to travel from an initial position to a final position. Horizontal and vertical lengths. So if I had to stay just horizontally and vertically to get to a place, that's all I can travel. I can't travel at any angles. I have to travel at horizontal and vertical directions. These are the components of the vector. Victor? Where I will use delta H as the horizontal movement from an initial position to a final position, and delta V is the vertical movement from initial position to a final position. So delta H is my horizontal movement, delta V is my vertical movement to go from an initial position to a terminal position. And we'll go through an example of it down here. Magnitude of a vector, once again, this should be reviewed for us. It's the length of the vector. Victor? The length of the vector. That is the magnitude of it. A unit vector is a vector with a length of 1 unit. So if I have a vector with a length of 1 unit, that is called a unit vector. Now, we have 2 special types of unit vectors. We have I, lowercase I, which is a horizontal unit vector. And J, which is a vertical unit vector. Now, those that have had physics class or taken physics, this should be reviewed for us. I is the horizontal unit vector, j is the vertical unit vector. So if we draw this vector here, we want to travel 100 miles and we want to go 30 degrees north of east. Well, on a coordinate plane, we can put some directions there. And we want to go north of east. So basically, if I took a look at a vector, here is going due east. We want to go north of east, so I'm going to rotate up here 30 degrees. And that would be a vector going 30 degrees north of east. And we're going to travel 100 miles. So that would illustrate a vector of 100 miles at 30 degrees north of east. We are traveling, we are starting here. Here's our initial position. Here's my terminal position. This is where we're stopping. Once again, we have to have a specific length, which is 100 miles. Now, for us to be able to write this in component notation, and that's what's going to be the main goal here, is to write things in component notation. We have two ways of writing in component notation. We can have these my less than and greater than symbols. I have my delta H and I have my delta V. Or I could write this in IJ notation, which is delta HI and delta HJ, or delta VJ. Now, how do I deal with components? I'm only allowed to travel horizontally and vertically to get from point A to point B. This here is my delta H, my horizontal component, and this here is my delta V, my vertical component. Well, what we have just done is traveling horizontally and vertically, we have created a right triangle. In this right triangle, my hypotenuse is 100 degrees. My angle is 30 degrees. I want to find delta H. Well, we have to ask ourselves, which trig ratio relates our delta H to this angle and this side and the 100? That's correct. That is the cosine. So we have the cosine of 30 degrees. I'm going to write down here. The cosine of 30 degrees is equal to delta H over 100. And to solve for delta H, what do we do to both sides? We can multiply by 100 times 100. So we have delta H is equal to 100 cosine of 30. So within my calculator, we have 100 cosine of 30. We get 86.6. And my delta V here, my delta V, the trig ratio is sine of 30 degrees is equal to delta V over 100. We can multiply once again both sides by 100. So we have 100 times the sine of 30. And my delta V comes down to 50. And these are all miles. So what we are doing is we're taking what this ends up being is we take a resultant vector and take it back into its components. Okay, so that's what we're dealing with in this case is we have a resultant vector. What would be the two components we can go? Which means my delta H is 86.6 miles. And my delta V is 50 miles. So what I would be able to do is I would travel 86.6 miles east and then 50 miles north, and that would be the same as going 100 miles at 30 degrees north of east. So in IJ notation, we can write this as this vector is equal to delta HI. So we have 86.6 I plus 50 J. Now, I and J are unit vectors. So their length is a value of 1. This is a scalar multiplier to that. So I'm taking the length of 1 and multiplying it by 86.6. Basically, this is just telling us the X is horizontal and the J, we are moving vertical. So I go 86.6 horizontally and then 50 vertically. That's what the IJ notation allows us to be able to do. Just write it so we can think about horizontal and vertical. PQ, vector V, PQ. We have the initial position is at point P, which is 1 and 5. Here's my initial position. And it also tells us here in PQ, when my first letter is first, my first letter here is my initial position, Q is my terminal position. So I start out initially at P, which is 1, 5, and then I travel to Q, which is at 3, -4. And that's my terminal position. So if I'm traveling here, I'm starting here and I'm going down and I'm stopping there. And remember, our arrow tells us the direction that we are following. So I'm moving from here down to here. And I want to write this in component notation. Well, if I take a look at this in component notation, I want to know what we are traveling. Oh, let's try that again. Horizontally, what are we traveling? And then vertically, what are we traveling? Good. So I want to know what we are traveling horizontally and then vertically to get from point A to point B. Well, I'm starting at 1 and I'm going to 3. So what we are moving is we're moving 2 to the right. And then I'm going from 5 all the way down to -4. So I'm traveling a total distance of 9 horizontally, but we're going downwards. So what I need to make sure of is I put a negative there. So I can write this vector, my delta V or delta H, which is my horizontal, is 2. My delta V is a value of -9. So in IJ notation, we can write this as PQ is equal to 2I minus 9J. Because I've gone horizontally 2 and vertically -9. We can also deal with this by just looking at components. We can go Y terminal minus Y initial. We can subtract these. My terminal position is a value of -4 minus 5 to get my -9. And my delta H, I can go with X terminal minus X initial to come up with this value also. My terminal position for X is a value of 3 minus 1, I get the value of 2. So that is another way of being able to do it. Terminal minus initial. Let's go ahead and do the next one here. And if we want to, we can do a picture. But as you get to this, you can also start looking at this idea, terminal minus initial. Once again, this is my initial, this is my terminal, because it just goes in order. So I start out at P at 0 and -4. X is 0, Y is -4. So I start here with my terminal or initial position, and then I travel from to Q, which is X is -1, Y is 2. Here's my terminal position. So we have to ask ourselves, what are we moving horizontally? And then vertically to get to those places. So once again, I could just look at it as a diagram, but we can also then take a look at terminal minus initial. So my delta H is X terminal minus X initial. My X terminal is -1. My X initial is 0, so we have a value of -1. And my delta V, we can go Y terminal minus Y initial. So I have terminal, which is 2, minus initial, which is -4. We have minus the negative, which turns into a positive. So we have 6. So in IJ notation, what we have is -1I plus 6J. We will stop there today. We're not going to continue on from this point. The worksheet I give you, you can work through the problems that revolve around this. We won't get to all the problems. Tomorrow's assignment, we will go on to the back side of this, and we'll take a look at the back side here, what we could do to deal with addition, subtraction of vectors, Victor. All I want you to do today, though, is the problems that deal with just what we talked about here. I'll post the worksheet, post the solutions. Tomorrow we'll go over the backside here. It's a little bit more material, and this will be the work for this week, just working through basic vectors, vectors. So Wednesday will be an review day. Thursday will be an evaluation. Once again, we will keep the same process that we've done the last couple of weeks. So if you have any questions about this, feel free to make some comments. I will help out as best as possible. But once again, just go through the worksheet, the parts of the worksheet that apply it to what we just have here. Tomorrow we'll complete the worksheet with the material that we have there. Other than that, I have nothing else for you. I miss you guys. I wish we were back in school, but we're not there. So this is what our reality looks like. So once again, try to continue to keep up with the material that I'm asking you to do here. And we are near the end. We hit May. There is light at the end of the tunnel here. Continue to do your work. Other than that, adios. I'm out here. Have a great day.